Good morning. Welcome to Krishna's class. Now we shall conclude our discussion on Hilbert spaces with a consideration of the Fourier series. Now, if you know the little bit of history of Fourier series, you know that it came up in the context of the study of the solutions of the heat equation. So that is where it all started. Something like this. This is the heat equation, and it was in the context of the study of the solutions of this that it was shown that you can use a formal series to solve or express the solution of this equation. Of course, there will be some conditions that come, but we are not going to the details of that. Now, it is very nice to have a look at this, because you know that the Fourier series also is one of the concepts which played a major role in the development of mathematics. In fact, it posed a lot of questions beyond the act of simply writing down the solution. If you were to make a rigorous study of that, then a whole theory had to be developed around the Fourier series. And in fact, that was a forerunner for what all things we. In fact, the study of L2 spaces was, and then the orthonormal sequences in the abstract form, or the study of Hilbert spaces as such, was prompted by the results that came out from the study of the heat equation, the solutions of the heat equation. In this context, the Fourier series came into being. Now let us just put together whatever we have done, and in this particular example, that will give you some insight into this. So you recall that L2T is the Hilbert space. All complex valued measurable functions on the interval minus infinity to plus infinity, which are periodic and with period 2 pi. That is the Hilbert space. We have defined it earlier. And with the inner product, this is the L2 space. It's a Hilbert space. Now, we have also had this, that UNT and belonging to Z. Z is the set of all integers, where UNT is defined as e to the power periodic functions. These functions have the property that this set of functions form a complete orthonormal set. This is what we have proved. Essentially, I mean, this is a very specific example, but in general, you have a Hilbert space, and then if you have a complete orthonormal set, then some nice results do follow. Okay, what are they? Let's see. Now you see that given f belonging to L1, L1T is with the that is 1 upon 2 pi this is the condition, and this is the one that we designate by norm of f. This is the one norm. So you take all complex valued measurable functions where norm 1 of f is finite, or periodic functions, of course. Then we have this is the L1 space, and for every f belonging to L1T, we have f hat n defined as 1 by 2 pi ft e to the power minus int dt. This is essentially the inner product of f with what you call un. And you see that e to the power minus int comes by taking the relation that this is integral minus infinity to plus infinity ft un conjugate t dt, or un conjugate is e to the power minus t. That is how it comes. And this is true, and this is well defined now. This is very easy to find out. Now you see that f hat n is less than or equal to 1 upon 2 pi integral minus pi to pi and if this is finite, then you see that this is very finite, because this is essentially the absolute value of this, and which is less than or equal to 1 by 2 pi integral minus pi to pi mod ft into modulus of e to the power minus int, which is equal to 1. That's why you get this relation. So this is well defined for all f belonging to L1. Okay. Thus, every n belonging to Z and f belonging to L1, we have L1T is F belonging to that, and this is mapped to and belonging to Z. This is the index. See, this is the index set that you have. Okay, and this you call what is called F hat. On Z. So you see that you can write F hat as which belongs to which is well defined, which belongs to what you call okay. Okay, so this is the identification. Okay. Now what we do next is this. Of course, you recall this result that what we have proved is if H is a Hilbert space, when a complete orthonormal set. Now by which you mean that this is a maximal orthonormal set. That means you cannot add in an additional function into that and get a larger orthonormal set. That is not possible. Okay, so if it's an analogous terminology that you have for maximality, there is the complete. So you call it a complete orthonormal set if it is a maximal orthonormal set. So once you have that and you know such things exist, then not necessarily U alpha, right? Say U alpha belonging to some index. Then what you have is this. What we have proved in the general case is that L2T isomorphic to L2. L2Z consists of all such elements of that. Okay. So this is the one of the theorems that or H is isomorphic to L2. This is the general theorem that where A is the index. Okay, for each Hilbert space can be put into isomorphism to L2A for some index set A. This is the central theorem that we have, and this is only a special case of that. Here A turns out to be, in this case, Z, and F turns out to be all L2 functions. Okay. Then the Fourier series for F for f is n. Okay, let us designate this by 1. Let us designate this by okay, and the partial sums are in, and this is for n equal to these are all the partial sums. Okay, now we say that how these from these partial sums you get hold of a function, the limiting process. Now observe that L2T is properly contained in and consequently all these statements do hold for functions in L. Okay, because the question of the existence of f hat n, all that you need is the function f is L1, but on T the function is also in L2T. That's what you have. Therefore, this is valid for f hat n is well defined for all f belonging to L2. Okay. One to every f belonging to this leads to what is called the Rees-Fisher. Rees-Fisher theorem that if Cn that means n running from minus infinity to plus infinity, all integers running from minus infinity to plus infinity, be a sequence of complex numbers. A sequence of complex numbers such that finite. Then there exists a f belonging to L to T such that Cn equal to 1 upon 2 pi what you are proving is the following. See, you have got on one side, you have got L2P as a Hilbert space. On the other side, you have got L2 Z. That's also a Hilbert space. Okay. What we are saying is that what we have shown earlier is that if you should start with an F, then Fn hat uh, Z now such that sigma finite. Now this is the forward result. The backward result is this. Suppose you have a sequence Cn, n belonging to Z, such that sigma n equal to minus infinity plus infinity mod Cn square is finite, then there exists a function f such that Cn is equal to this one, that is, this is essentially Fn hat. Okay, so either way it is true. So you see, for each f belonging to L2, you have a element in Cn. Conversely, you have an element in L2Z. Conversely, for each element in L2Z, you have a corresponding. This is what is the content of the Rees-Fisher theorem. The Parseval theorem says rather asserts that plus infinity conjugate. This is equal to 1 upon 2 pi where both f and g belong to L2. Now you can show that this integral exists because if you just use what is called Schwarz inequality, because you know that this is both f and g belonging to L2, therefore this is true. Norm f2 is finite, norm g finite, and you have modulus of 1 upon 2 pi minus pi to pi norm of F2 and norm of G2. So this is the Cauchy-Schwarz inequality. Now the series see what is the result that we have okay. Now the series, I will just designate this by 6 and this by on the left hand side of 6 converges absolutely. Again, it can be proved using the Schwarz theorem. Further, we have limit n tending to infinity of norm of f minus zero ascendance to this is something that you can do because you already have ascent. Yeah, where have I find it? Okay, so where of course I defined it earlier ascent. Where for each n for each n small n greater than n of full square. Now, to see that this one, you look at this. See, this is what you have. We have this convergence. Minus infinity, plus infinity, finite. Okay. So you see that this is the tail of the series, and this can be made arbitrarily small by choosing n sufficiently large because of the convergence of this. And recall that we have chosen Cn such that Cn square is finite. So this is how we, and this is the Cn's turn out to be simply your f hat ends in this case. Okay. So this we designate by 7. So it is by 7. F belonging to L2 T is the limit of the L2 limit of the partial sums is. That is the Fourier series of f converges. This is the important part, is the L2 limit. It's not pointwise convergence that you are talking about, but this is the L2 limit of the partial sums of the Fourier series that you have, and that's what we here. This is the L2 norm in which this convergence takes place. Now, this is essentially the distance d2 of f. Okay, so that is the metric induced by the norm in L2 is this d of fg2. This is the metric that you use, and that's what you have here. So f and Sn converges to f in the L2 sense. Now, if you want to discuss a more stronger type of convergence, in the sense that if seek pointwise convergence, then it is a more delicate you observe the following. See, what we have obtained in the general theory of Hilbert spaces is what is generally called the soft analysis. But you really need some minute, finer analysis if you want to look at this problem of pointwise convergence. What is the pointwise convergence? That each point ft converges to, or SNT converges to ft. Okay. So if you are asking for pointwise convergence, then it's altogether a different problem. Now we will just conclude with the Viswa theorem. The reason and the Viswa theorem The Parseval's theorem says if you take L2T and then take an element of that F belonging to that, then this is put into one-to-one correspondence with F hat So what you have is this arrow either ways point out that given f hat belonging to L2 set, you have a corresponding f in L2. Conversely, given an f in L2T, there is an f hat belonging to L2 set. Or this is what we have proved that L2T is isomorphic to L2 set, or the general version is H is this is what we have proved earlier. So this is the version of that. Okay. And one remark about the Parseval's theorem. The Parseval's theorem actually gives you, that is f therefore what you have is you put G equal to F, this is what you end up with. Full square at n square. Okay. Now, what does this mean? This is essentially a generalization of Pythagoras theorem. Pythagoras theorem. Okay. If you examine Pythagoras theorem, this essentially is an infinite dimensional version of the Pythagoras theorem. The norm of f is sum of the squares on the of these sides is equal to the diagonal. So you have, for instance, in R2, this is what you have. If you take in R2, take E1 and E1. You know that the usual inner products they are occur. Okay. Now you take any vector. So this can be resolved along this direction. So you have what you call C1 E1 and here it is C2 E2, where this length is equal to C2, this length is equal to C1. So what about this? This is the length of the vector. So the length of the vector, and you see that C1 is essentially x E1. Here you are using the powerful relation of orthogonality. C2 equal to E2. So what you have is, if you call this the vector x, x is equal to C1 E1 plus C2 E2, which is equal to the inner product of x E1 E1 E2. And what do you have? Norm of x square equal to mod this is essentially the Pythagoras theorem in two-dimensional space. And you know that Ei, Ej, that is E1 that means E1 E1 is 1, E1 E2 E2 is 1, and E1 E2 is 0. So we have this result, and this you compare with what you have here. Okay, this result, okay, or the outcome. That is the Pythagoras theorem. It's essentially the Pythagoras theorem. So you see that you carefully search for the root of many of the high sounding results that you see. They are essentially worthwhile generalizations of something that we are familiar with. In fact, my advice to students would be that if you are learning functional analysis, then you should be quite well versed with R2 and R3, or any result that you come across in Hilbert spaces or Banach spaces or general non-linear spaces. You should look at the analog of this in R2 and R3, where you can visualize it. So you get a wonderful feeling of what these results are. Otherwise, what happens is they will just go into your mind only as an abstract entity. But that is not the case. Now, here you can compare this with this one. Okay, you can see this what you are getting. Okay, this you can write as x hat 1 same notation. Okay, so this is what it turns out. So you can see that in the proof of Viswa theorem, the proof of the Viswa theorem, we use the fact that let me put it this way. Let's give an example. Consider R3. R3 you know, and the inner product of xi yi, where x equal to y equal to y3. This all expressions with respect to, so you are having, see, this means the following. Now you see, you have E1, E2, E3. This is an orthonormal. It is complete also. It's complete. But you see, if you just take E1, E2, this is an orthonormal. In R3, which is not complete. So you can find another vector E3 such that the larger collection that you have is again another orthonormal set. So it is not, this is not maximal, therefore this is not complete, and you cannot use this to express an arbitrary vector in X. For instance, what you get if you just use this one, what you get? You get X hat E1 now you see that X is not equal to, in general, I am telling in general, X E1 E2 not equal. You see that therefore to write a result of this kind, you need if you want to write down the Rees-Fisher theorem, then you need the completeness of the orthonormal set, and this is what you mean. So this is what I said. You should go to the grassroots, elementary but non-trivial examples where you can actually visualize things and try to understand the problem and the result. Even before you jump into the proof of any theorem, you should take good, credible, simple examples where you can visualize concrete examples on which you work. In fact, Fourier series is a concrete example of a Hilbert space. So you see, the general theorem that we have proved is just condensed out of or inspired. The inspiration came from Fourier series, and the insights also came from Fourier series. Okay, and if you go back to the roots, you see that it is there in R2, R3, and so on. Okay, so that's what I wanted to emphasize. Now I want to make a remark finally. Sometimes the result that L2 Z is also called the Rees-Fisher. That's a remark. With these remarks, let me conclude today's lecture. So that is a very short lecture, which concludes our discussion on Hilbert spaces in the context of the abstract integration theory. Okay, thank you very much. But the key to learning mathematics is taking good examples and analyzing. Thank you very much.